Hi everyone, welcome to the channel here, Becoming a ROS Developer. Today we're here with Tomás, who is going to present to us his project for ROS Basics in 5 days, in which he uses a Turtlebot to create a series of movements based on the creation of topic, subscription, and publishers, as well as services and actions. So, hi, Tomás, how are you doing?
Hi, Rodrigo. How are you?
Good, good. So we're just gonna go over your project, and we're gonna go ahead and try it on the real robot as well. You should be able to connect whenever. If you wanna share your screen, and then let's begin.
All right. Here we are. Okay, please let me know if you can see the screen.
Let me see. Yes, we can see it.
Okay, I'm sharing a short presentation, and in the middle, we'll be moving to the real robot. So I think this is a more organized way of presenting the code, which is of interest in this presentation. So, okay, hi everyone. My name is Tomás Liendro. I'm a mechanical engineer and robotics enthusiastic. I am from Argentina, and I'll be presenting to you the ROS Basics in 5 days using Python and the Turtlebot, which is here in the right side. So along this presentation, I'll be showing you a short introduction of what this project is about, and then I'll go over the 3 parts of this project, which includes, as mentioned before, topics, publishers, and subscribers, services, and actions. So just to give a quick overview, the ROS project I developed is named ROS Basics Real Robot Project, which is basically a wall follower project in which we'll be using this Turtlebot 3 robot to follow the wall to follow a wall using a LiDAR, and then we'll record some odometry. We'll be developing, as mentioned before, the 3 parts using Python, and everything I did, before moving to the real robot lab, I make sure it works in the simulated environment, which is very important in order not to break anything. So the Turtlebot has a LiDAR on the top side, and the motion is a differential motion, just for understand how it works. So let's move on to the part 1, in which we develop some topics, publishers, and subscribers to make the robot follow the wall. The basic idea is to keep the robot within a range of 0.3 and 0.2 meters from the wall. And to do so, we'll use the laser topic, which basically captures the rays from a LiDAR sensor. And one item here important is that when it reaches a front wall, in case of the corners, we'll make a short, we'll write some lines in order to make this transition smooth when the robot has to take the next wall. So the first thing we did here is we need to understand what is being published in the scan topic, which is the one that contains the information from the LiDAR. So using the ROS topic info /scan command in the command line, we can see this topic contains a message from the sensor message /laser count type. Then we can see what kind of information is stored in this message using the ROS message show and the name of the message. And we can see that all of these variables are inside. Particularly, we are interested in the float 32, this array named ranges, that stores the measurements of the LiDAR sensor. And that will be the one that we'll be using to navigate through this environment. So the next thing we have to do is to understand what is being stored here. So basically what I did is put the robot in front of the wall and take the measurements that are inside and take record of these ranges array. And I did it for two positions. Position 1 with the robot in front of the wall, and position 2 with the right side of the robot in front of the wall. What we see here is that the minimum position is given for the position 1, for example, which is the blue line, for the index 180. And for the second position, it's on the 90 index. So this is important for us because we're using this measurement to measure the distance from the wall, and then we can move based on that information. Another thing that we'll be using is the command bell topic, which is of type geometry message /twist, and contains this a linear variable with 3 components, x, y, and z, and the same for the angular velocity. This command bell topic we'll be using to command the motion of the robot. For example, if we write a set point, for example, 1 in the x component of the linear, the robot will be moving in that position.
Right.
Okay, so let's move on to see the code. And the first here in the right side, in the left side, sorry, we can see the launch file, which we'll be using to launch the nodes that executes the script. Here's the name of the package. I think it will be easier. Okay, then I'll do that. We initialize and in this case, we have the Python script that will be performing the wall follower command actions. I mean, so what we have here is this is the same, but with nodes on the side. What this script does is initialize the node, which is specified here in the launch file. Then we create a subscriber to the scan topic, which is of type laser scan, and every time it receives a new data, it will be running the callback action defined here. Callback function. Then we set the loop rate, which is 5 Hertz in this case, which will be the refresh rate. And then we create the publisher. Basically, the publisher will be is an object that will be submitting commands to the command bell topic in this case, which is of type twist, and it will be sending one command at a time.
Mm-hmm.
This we create also this move variable, which is of type twist, to store the information that we will be sending to the command bell topic. And then we start the loop. Inside the callback function, it's really simple. We just take the 19th, sorry, the index 90 from the ranges, which is the measurement of the LiDAR. And if it's between 0.2 and 0.3 meters, it basically moves forward. And if not, it tries to compensate it by adding some rotational speed to one side or the other one. For the smooth transition between when the robot reaches a corner, I did this small if condition lines in which the robot basically keeps on moving, but keeps moving, but in a slow linear velocity, by adding a bigger angular component. And just for preventing the robot to get stuck, I wrote these lines, which basically makes the robot moves backwards when it gets too close to a wall that we can consider the robot will not be able to escape or to keep on moving. Basically, it deviates, it goes back a bit until the robot can keep on moving.
Right. Oh, nice. Nice addition there.
And finally, I mean, with all these lines, we set the set point that the robot has to receive in the command val topic. So we publish in the cmd val topic with this final line inside this function. Here is a short animation of what the robot does when when we run in the simulator environment. I mean, then we can see it in the real robot lab, but just to keep on this philosophy of testing everything in the simulated environment before moving to the
that's good.
Real robot lab. So here you can see that it avoids these obstacles in the middle, and then it tries to restore its position to keep the distance from the wall. And I think we can see there the smooth transition, and that's okay.
Great. So maybe we can go ahead and if you're in your ROSject, we can connect to the lab and try it there.
Okay, sure. Let me see.
Okay, we're connecting.
There we go. So let me see if we can connect. Isn't connecting?
Okay, I think now that the lights turn green, maybe you can try the joystick again and just make sure.
Yeah, perfect.
Okay, great.
A fantastic tool, the joystick.
Yeah, I know, right?
So we'll launch and this is the wall follower command. We should be seeing that the robot follows the wall.
Oh, there he goes. And will it do just an infinite number of laps, sort of following the wall forever?
Yes, in this case, it will keep on moving. For the action, for the last part of this project, I was working on stopping the robot when it reaches a complete line.
Right.
Maybe the reason why it's moving like so far from the wall is maybe we can adjust the ranges.
Yeah, that's probably. But I mean, will it stop? So does it take into account those obstacles, or sort of it will get confused with the wall?
Yes.
So right now.
Yeah, like that. What I also found out is that I will stop this robot from running and just want to make a parenthesis here. Is that something that I found out is that the measurements of the LiDAR got a bit noisy for some positions. For example, as you can see here, I mean, this is on the simulated environment, but it also happens for the real route lab, in which for some index, it got like noisy, even if there's nothing around. So I know there are some things we can do to make the system more robust, like for example, filtering this information, or just setting a value here just to make the robot to ignore them, those values, and avoid the confusion. I don't know, maybe those are some things that I've been thinking about. But
yeah, and you said this happened in the simulation as well? That noise?
Yeah, yes, as you can see here, for example, in the position 2 here, this corresponds to the orange
right, yes,
curve, and you can see that there's nothing, like
it starts increasing and then it drops to 0. Yeah,
and it really drops. I don't know, maybe I couldn't study it in depth, but I was having some issues with this. Maybe this is not the most robust solution, but it at least,
if it works, it works. You know,
it worked in a range.
Right on. So great. You want to move on now to the service part?
Sure. Yes. There we are. So in the second part of this project, we had to create a ROS service server that, when called, it will make the robot to go to the nearest wall. And we'll be modifying part 1 and create a launch file for executing both nodes. So regarding the services, we created a service message, a service actually. Here is how the configuration was done. We have to create a new folder in our project folder. Here is how we included all the. Here is included the service in the CMake list file, which will be used to compile and execute everything. The service structure has a first part, which is the request message. In this case, it was left empty. When the service is called, it won't be requesting for any input argument. And the service response message is the second part, which basically is a Boolean variable that says if the robot has reached the wall. This is the service server code. Okay. The service server basically executes, starts the node here. It declares a move variable, just as we did before, which will be used to publish on the command vel topic. Here, what we called the serve variable basically initialize the service, which is called find wall. It receives a request message of find wall, and it returns a find wall callback. Okay, and then we initialize a publisher, just as we did before, to send the commands that will move the robot to the nearest wall.
All right.
Here's the find wall callback, which is a function that will be executed when the service is called. We have to put it in the while loop, and what it does is basically takes the minimum, the index of the minimum value in the ranges array, which is in the laser scan, which is a measurement of the LiDAR. So we detect where is the minimum of that measurement, and we take the index of that. We'll be using that to rotate the robot until it is facing the wall. The front of the robot is facing the wall. When it does, it means that we are here, and the robot will move forward until it reaches a position, the position of less than 0.3. This line basically says that when the front of the robot is less than 0.3 meters, it will stop. It will stop moving. It will publish on the CMD bell topic to stop moving. And then it will prepare the robot in the sense that it will rotate until the right side of it is facing the wall.
Right.
Which will be presenting the robot, which will be letting the robot start the wall follower motion.
Great.
Here are some. And this is the service client, which we'll be using to call the service that I mentioned in the slide before. Again, here is the client initialization. Sorry, it initialized the node. It waits for the service, which was defined in the previous slide. It connects to that service, and it basically creates an object that will be the request message, which in this case is an empty variable, and then it executes. It calls the service. Again, we have to create the subscriber and the publisher for running the same algorithm that we did the same algorithm that we did in part 1 to follow the wall. And then finally, the launch file is this. We first initialize the service server, and then we execute the command robber and client, which is basically this service client script. Again, what we have here is a short simulation of what we did. We can directly move to the real environment.
Yeah, I think we can.
Yes. Okay. Great. So it's in.
So then this is the launch that launches the server and the client. So it's going to start looking. There you go. Starts looking for that wall.
Correct. Yes. There it's trying to
find it. Maybe it's not finding it because there.
Yeah, it's because there's it has to be exactly half of the range.
Yeah, you only take one value, right?
Oh, nice. It died. Yes, that's why it takes a while.
So
signal cannot.
Got a shutdown request.
Yes, I don't know what's going on here.
Maybe it's because the number of values in the real one is actually, I think it's 720. So maybe it's not in the simulation. I think it's 360. So
yeah, what it does is to take to measure the length of the range vector array, and then it divided by 2.
Oh, okay. So it doesn't matter.
Yes. I don't know. I got a request. I'm trying to find which is the line. It's like action client.
It never received that response, maybe.
Sorry. Yeah, it reaches up to the point of preparing the robot.
So let's just launch it again and see if it happens again.
Okay.
So there is rotating, looking for that, because it already found the minimum.
Yes, and then
it goes the other way. Oh, because now it's preparing. Okay, now it's getting prepared because it's going to start following the wall because it's inside of that. Oh,
There it goes.
There you go. So then you put the find the wall and then start the follow wall inside of the client. So it does it all in one. Correct?
Yes, it's on the client.
Uh-huh.
And the client calls the service before following the wall. Maybe I can minimize. Okay, and then it does like.
It will go. Okay. Oh, maybe it's gonna run into that.
Yeah. Oops. I'll stop it because I'll make a mess of your.
That's fine. So then, modifying those values would make the movement tighter, right? Like closer to the wall, correct?
Yes. Yes. Correct. Maybe I lost connection. No. I'm not being able to comment. Yeah.
Oh, it's not moving. Go to the terminal and check. Did that?
It is.
Let's see if you see the topics. Maybe it got disconnected, but.
Okay.
Huh.
Scan. Yeah, I can see.
It's right there. So maybe the joystick got.
Okay, maybe I can move to part 3 and refresh this site, because
while you're explaining the next part, try disconnecting and connecting again, because maybe that joystick got.
Okay.
So yeah, and it'll take a while, and then you can start the part 3, and then we can try it.
So the final part was to implement actions, to record odometry, and to measure how far the robot has been moving. So actions, basically what led us to is to run simultaneously some scripts, some actions, unlike services, actions are non-blocking features of ROS, which are great for performing several tasks at the same time. So the structure of an action message is as shown here. This is the name of the action, odomrecord.action, and it has three parts: a goal part, where that is basically what the client sends to the action server. Then a result, what is going to be the last thing returned by the service action server, and a feedback that is something that we will be using to continuously be monitoring the distance traveled so far. So we created this action folder inside our project directory, and here we can see also the configuration, the CMake list, where we should be adding the action message files and the dependencies. Okay, in our case, in our work, the list of ODOMs, which is the result message, basically when the robot has complete a lap, it has to finish and return the list of odometries recorded. So it's an array with the list of odometry that the robot has registered. And the feedback message provides the total amount of meters that the robot has moved so far. So it's something that will be looking continuously on the screen. Okay, this is the action server. The action server, for the action server, we defined a class because it basically let us organize better the code, the scripts. And there's a second part of it. Yeah. It's better if we start here. Here, start the action server. It initializes the node. It initializes a publisher. And then it calls the Turtlebot 3 class, which is the one that I was showing here. The Turtlebot 3 class basically has, again, the init part, it starts initialize the variables, and it calls for the action server that is called /record.on. And it starts the action server. I cannot see, where is it? Here's the goal callback, which is that will be executing by the time the action server is initialized using this start command. So the goal callback is where the magic happens. Mm-hmm. It initialize a list of odometry will be the feedback message, a odometry message, which is let me remember this wait for message. Yeah, it's subscribed to the odom topic, sorry. Then we take record of the initial position and initial odometry of the robot with these lines. And we append that values, those that odometry, that initial position in the list of odometry. And we define a Boolean variable that we called checklab to see if the robot has completed a lap. So it starts in this while loop. Then we will come back to see what these two functions are, but we'll go into the while loop, which is the one here. Here in the message variable, we store the odom topic. Yes, the odom topic, and we take record of the current odometry of the robot. We check if there's a cancel, if the client has requested to cancel the action server. If not, we move on, and we call this compute odom function, which basically takes the measures the distance between the old odometry and the current odometry. Mm-hmm. And the old odometry is the previous step, the previous measurement. And in the feedback message, it basically sums up the current the odom metrics, which is the distance traveled before the last step of time and the current one, and it sums to the accumulated odometry traveled. And then it publishes the feedback message in this action server. It prints on a screen the total distance traveled in meters, and then it checks if a lap has been completed after if the odometry is more than 1 meter, if the distance traveled is more than 1 meter, it starts checking if the robot has completed a lap. And the check lap, and for checking if the lap is completed, it takes the measurement between the initial position of the robot and the current odometry. And if the distance is less than a defined radius, which in this case is 0.2 meters, it stops the robot.
It's
by
considered
publishing
a
0.
full lab.
Sorry?
That's considered a full lab once it enters that radius, that circle that you defined in there.
The fold up, what is that? Sorry.
So you said you defined a radius.
Yes.
And that's once it goes into that circle, then that means that the Turtlebot has finished the lab and will stop, correct?
Yes, correct.
Okay.
Yes.
Great. Do you want to go ahead and try it? We got like 10 more minutes, so maybe we can.
Yes. Yes. Here is the action client, but it does not add too much. Basically, it adds how the action client is initialized, but we also have the service and the publishing subscribers and the well follower commands.
And then you include it into, yes, okay. You include it into that launch file.
Yes, all three parts are running in a single launch file.
Mm-hmm.
And the last part that is called is the client, which is obviously. Okay, here, well, we can move and try on the real robot lab, but it was tested.
Yeah, let's try it on the robot, and if it doesn't work, we can run the simulation and try it there.
No.
Or, I mean, look at the video that you prepared for us.
That should happen. Ah, there it goes. Mm-hmm.
So remember.
Yeah.
There you go. Yeah, see, it was before. I think the joystick got disconnected somehow. But okay, we can.
We'll try to move it a bit away from
the obstacles.
Yes. Mm-hmm. Oh, come on. There it goes. Okay. We can try that. It's launch robot 3 lab, and this is called main with actions. And let's see.
Let's see if the odometry is working or not.
Okay, now it's performing the
finding the wall. Okay, now
yeah, it's finding the wall.
Turning 90 degrees.
Until it reaches, I think it's 180. That's 1/4 of the range. And okay, it's not recording odometry.
Yeah. And that's because the motors are having an issue. So the odometry topic is not working. So let's just look at that in the simulation side.
Okay.
So, but I understand the process that the odometry would be showing up there. So if you want, you have a video, right, that you prepared?
Yes,
you could also show us that.
Okay.
It's a little easier, less time consuming.
Yes. Okay. It is still not working, not running, I mean. Now the server is connected.
Uh-huh.
Yeah, maybe it crashed the first time. Yeah, it crashed the first time.
Always happens.
Okay, there it goes. It does what we were seeing on.
Yeah, exactly the same thing, except since the odometry is working here.
And
Right.
okay.
It starts spitting it out.
Yes, I thought it was some issue with the refresh rate. Maybe this is why it goes like too slow. The refresh of the information, because I was trying to debug what was going on the real robot lab.
Yeah, no, it's an issue with the motors. Just the odometry, sometimes it just goes away because it's running 24/7, and it's something we have to fix.
I guess. Okay, and you can see here that after the odometry is larger 1 meter, it starts checking if it completed a lap or not by returning this Boolean. In this case, it's false because it didn't get a complete lap. But we can like speed it up a bit and see. Oh, not so far. And it completed a lap, and then it should be like checking. So here it says the distance to initial position is going down.
Oh, right, it's getting closer.
1 foot, and then it arrives. What I didn't get to work is to stop. I don't know why it keeps on running. I think it's because I couldn't like stop the node or stop the wall follower.
Oh, but I thought you included that like a 0 message in your client, in your action client.
Yeah, that's correct. I mean, I put it here in the action service. When it completes a lap, which is this line, it publishes on the command val.
So yeah,
it publishes 0, but I don't know why this is still running in the client. I think it's something that it is not being stopped here, but I didn't get to.
Okay.
To what was going on.
All right. Well, let me ask you a couple of questions because we're running out of time here, and I just wanted to ask you a couple of questions. First of all, I really like that plot. How did you make that, the position plots in the beginning that you showed us? That one, yeah. How did you make that?
Yeah. I did it by typing ROS topic echo the scan topic, like this, by using this command. It gave me
one message,
all the or maybe we can do something like that, and then I just plot this this array using Excel.
Oh, nice. Well, it's really helpful to understand what you're trying to do there, so I noticed that you also added classes into the action section. Is there a reason why you kept it only to the action, or would you have benefited from using it from the start? Or did I see wrong and you did use classes for the first 2 sections?
No, I just did it for this third part.
Because it started to get more complicated, no?
Yes. This was some attempt of organizing better the code. As you know, I learned classes in this project, in this tutorial and this course, sorry. And yeah, this was some attempt of making an effort to learn how to use classes.
Right.
But I found out that they are really, really useful for this organization.
They are, and I'm just saying it because I understand why you didn't do it in the beginning, because you don't need it for like short programs, but I would recommend you to stick to once you know how to kind of implement the classes, because as soon as it starts getting complicated, if you're working on a project yourself, you'll wish you used classes. So
Yeah, yes.
And I mean, other than that, I think that's it from my side. Do you mind stop sharing your screen?
Okay. Stop sharing.
Let me just get this back to our faces. All right, yeah. So, good job, Tomás. You did pretty well in those cases. And the last thing I wanted to ask is there a way you can think of that you would have been able to account for those obstacles? Because it would have kind of with that program you had, it doesn't know if it's an obstacle or a wall. Is there a way that you thought of looking forward to improve it, to consider the obstacles and be able to recognize, okay, that's an obstacle, that's not a wall, so it doesn't get confused?
I think that the difference between an obstacle and a wall is that the wall is some continuous thing, and maybe in the LiDAR measurement we can see like some smooth transition between the minimum and each side of the measurement.
Right.
And an obstacle will be something like a spot or a peak, or I don't know how to explain, but like
it would have a big drop.
Local.
Yeah.
Yes, that is. Maybe the way is to analyze the side values.
Yeah, or instead of one value, looking at a full range of it and kind of try and figure out that way. I'm just mentioning it because it's always helpful to think of those things to improve upon what you've done. But anyways, Tomás, we're running out of time here, so I wanted to thank you for presenting here with us. I hope you found this course and project helpful, and this is for everyone else watching this. This can be you, so I encourage you guys to take the course and present here with us, and the presentation is sort of the last step in order to get that learning from the course and be able to use it in your personal projects or wherever you want it. So thank you so much, Tomás, and hope we'll see you around here for other projects you can have coming.
You will. Thank you.
All right, so see you guys. Thank you.
See you.
Okay, ya terminé.